Everyone, welcome back to Code Happy 101. Today we're diving into the fascinating world of rate limiters in network systems. Have you ever wondered how large scale services like Twitter, Google Docs, Instagram, Facebook manage to keep their systems running smoothly despite receiving millions of requests? The secret lies in a clever mechanism called rate limiting. Let's explore what it is, why it's crucial, and how to design one. Let's do it. In simple terms, a rate limiter controls the rate of traffic sent by a client or service. Imagine you're managing a popular API. Without rate limiting, users could overwhelm your system with requests, leading to downtime or poor performance. Rate limiters cap the number of requests a client can send within a specific period of time. If the limit is exceeded, excess requests are blocked. Couple examples would be a user can write no more than 2 posts per second, or you can create a maximum of 10 accounts per day from the same IP address, or you can claim rewards no more than 5 times per week from the same device. As always, we begin a system design session by clarifying the system requirements and scope. This will help us stay focused within a short window of time we have. If this was between you and the interviewer, you might have the following clarifying questions. What kind of rate limiter are we going to design? Does the rate limiter throttle API requests based on IP, the user ID, or other properties? What is the scale of the system? Will the system work in a distributed environment? Is the rate limiter a separate service, or should it be implemented in the application code itself? And finally, do we need to inform users who are throttled? Now, from our clarifying questions, we can now synthesize the functional and non functional requirements. The important thing here is to make sure that you and the interviewer agree to these points. In this case, the functional requirements are creating a system that limits requests based on IP address, user ID, or any sort of IDs. And the non functional requirements are the system has to be highly available, scalable, and fault tolerant. As you go forward in the interview, make sure to refer back to these requirements as they will help you guide your solution. Make sure you meet all of your functional requirements first in the high level design, and then move on to your non functional requirements in the deep dive session. More on that later. There are many rate limiting algorithms, such as the token bucket algorithm, the leaky bucket algorithm, fixed window algorithm, or the sliding window algorithm, and many more. Each algorithm handles request limits differently. We won't be going over all of them in this session. Instead, we will explore the token bucket algorithm. Imagine a bucket with a predefined capacity. Tokens are added periodically. Once the bucket is full, extra tokens overflow. When a request arrives, if there are enough tokens in the bucket, one is removed and the request proceeds. If there aren't enough tokens in the bucket, the request is blocked. The token bucket algorithm is widely used and allows for a burst of traffic for short periods. There are two important parts of the token bucket algorithm, and that's the refill rate and the size of the bucket. The refill rate is how many tokens are added per second, and the size of the bucket is the capacity or max number of tokens that can fit into the bucket. Let's go over a concrete example. Let's say at time two, there are 3 tokens in the bucket. And let's say at that moment, 3 concurrent requests arrive. Now, given that there are tokens in the bucket, all three requests will succeed and each will take a token with them. Then let's say another request comes in a millisecond later. This request will fail because there are no tokens in the bucket yet. And that's the token bucket algorithm. Now we can move on to the high-level design. The purpose of the high-level design is to meet all of the requirements agreed to between you and the interviewer. Start simple and meet all of the functional requirements first. Then you can move on to scaling up and identifying bottlenecks and areas to scale in the deep dive session. For our high-level architecture, we'll use an in-memory cache like Redis to store token buckets due to its speed and support for time-based expiration strategies. Here's a simple workflow. A client sends a request to the rate-limiting middleware. The middleware fetches the token bucket from Redis. The middleware checks if there are enough tokens in the bucket. If tokens are available, the request is forwarded to the API servers and the tokens are decremented accordingly. If the tokens are not available, the middleware returns a 429 response to the client. If the request is allowed, the response is sent back from the API servers. If the request is rate limited, HTTP response headers like X rate limit remaining and X rate limit retry after are included to inform the client about the rate limit status. Tokens are replenished in the bucket at constant rate, ensuring that the rate of request processing does not exceed the predefined limit. You can have rate limit rules and store them in disk and frequently pull them into the cache for real-time access. Great work. To wrap up, we've covered the basics of rate limiting, its benefits, design steps, and algorithms. Remember, designing a robust rate limiter ensures your system remains responsive and cost-effective. If you found this video helpful, don't forget to like, subscribe, and hit the bell icon for more tech insights. If you want to see specific system design videos, comment below. Thanks for watching. See you next time.